Okay, this next lecture is about principle of virtual work for matrix analysis. If you have been following my lectures, you know we're really worrying about how to get EK. Okay, but you know, just to remind you, like, what is EK? EK is element stiffness matrix. What it does, it's basically a relationship between the force vector and the displacement vector of an element, and in fact, it's we'll see if for an element in equilibrium. Okay, that's you see this word, you're like, okay, well, that's probably where principle of virtual work came in. Yes, and those guys, because when we do principle of virtual work, if you review my notes earlier, you know you need a real set of forces and stresses, and you need a virtual displacement, and then make them do work, and then make them equal to 0, and all that type of stuff. So those guys, for a element, those guys are real. Okay, so when you have an element, I don't care what it is. I mean, it could be a bar, it could be a blob. You define the nodes, and then you apply some forces, and then you measure the displacement. Yeah, if it's in equilibrium, it's real. So the idea is like, well, how about we apply a virtual displacement on the element. Then you're like, okay, how do I do that? Oh yeah, in fact, if your real displacement for an element is being discretized in each node as you know, f vector and then a delta vector, the virtual displacement is simply a delta. Yeah, so it is a vector that encompasses all your degree freedoms, and it's virtual, and it can be anything. So let's see if we do that, how could we write out principle of virtual work statement? So we have virtual statements here, virtual displacements here. So all we need to do is just do the external virtual work. In this case, for the element, you know, we don't need to worry about boundary condition anymore. Why? Because any number in the displacement vector, it works. Okay, there's nothing restraining it from doing anything. So the virtual displacement can be anything, and then the only external force that's done virtual work are the nodal forces. So it's simply, if you think about it, it's just F times this. By times, what I mean is really you need to flip your F this way, F1, F2, all the way. Depending on, let's say if you have an n degrees of freedom system, then times the virtual, you know, virtual delta 1, delta 2, all that type of stuff. Then you just time each one of them and add them together, right? So yeah, if you really want to write it, it's really like Fi delta I from 1 to how many, the number of degree freedom you have. Okay, that's all cool. But then, in fact, if you define a degree of freedom of an element, you can just write this, just no problem. Then you're like, oh, okay, how about the beams? We have rotation and moment. Yeah, it's the same, because the whatever, if there's a moment m here, like m here, then your delta here will be theta, okay? Then the moment doing work on rotation. So yeah, it still works. The really challenging thing is this part, internal. And we know it's basically the integral over the volume of real stress, which, you know, we don't know, and times virtual strain, dV, okay? So the rest of this lecture is gonna kind of guide you step by step on how you actually do this, how to formulate principal virtual work in a matrix format. But let's kind of look at the big picture here. So we have this guy is the real stress, right? So real stress, we can somehow calculate it using real strain, right? So somehow we can calculate real strain using the theory of infinitesimal strain with real displacement. What is real displacement? It's this guy, okay? So basically, what I'm saying is you could somehow write the real stress in as a function of your real delta. So apparently your virtual strain is related to your virtual displacement. That we know. And the principle of virtual work is actually those two guys to be equals together. So what you have here is external, which is equals to somehow F times this delta, something like that. And then it is equals to the internal thing, which is some function of real delta, yeah, and I'll just say times, but you know, it's not exactly times, but times something like E, G, those material property. And then somehow times this virtual displacement. Yeah, because virtual string is actually a function of virtual displacement. Then, since those two guys can be anything, if you get rid of them or just assume they are anything, so that you can get a relationship. So what's left is the relationship between this guy and some E, G, some material stuff, and then times a function of this guy. So you got a relationship between your real force and the real displacement. And then if you arrange this blob in a matrix form, that becomes your EK. Okay, yeah, that's a big game plan. Okay, that's a big game plan. In fact, this big game plan it applies to not just matrix analysis. It applies to every single finite element stiffness matrix derivation. So it applies for bars, it applies for beams, it applies for planar element, plates and shells, solid element, anything. So one thing that's not so clear at this point is, yeah, how do you do this blob? Like, how do you write this as a function of this, and how do you kind of incorporate those material properties in there? That's what we're going to talk about step by step. But first of all, it looks like we should start by trying to somehow relate real displacement with your element, displacement vector. Let me say that again. We should find a way to relate your element displacement vector to real displacement. You're like, what's real displacement? Okay, real displacement is this. If you have an element, and then you define maybe, just for illustration, you have 3 nodes, it's 2D, you have your delta will actually looks like x1, y1, x2, y2, x3, y3, and they can take any number that will stretch your element in each way. What do you mean by relating this to the displacement? The displacement, like I said, is actually a displacement function. So that is basically the if I establish a coordinate system x and y, and then I pick a point P in here, and I find out it's x and y, I should have in 2D case, we should have a u of x, y, that if I plug in x, y over the P, it should give me how much P moves in the x direction. Then I should have this thing as well. I know it's kind of confusing a little bit because you have a vector here, those are actually numbers. Then you have like two functions here. Those are actually variables inside the function. They are actually not the same. So how do you make this connection? That's what we're going to talk about next lecture. We're gonna start by introducing a displacement function for the bar element, which is axial force element. Then we're gonna do that for the beam element, and then it is going to be done through a very extremely important. There's probably nothing more important than this in this entire EK thing, infinite element as well, by introducing a concept called shape function. Shape function z. Yeah, you have to have multiple of them to make it work. Okay, we'll see you on the next lecture.